Right, this video is about fluids. It's Pascal's principle, buoyancy, buoyant force, and apparent weight. And let's start with this container here. It's a tank that has five different distinct openings. So we have a couple of cylinders. This one's angled, this one's thin but straight up, and this one's wider uh, cylinder here. They're all open to the atmosphere. This one is kind of like a cone, and then this is just like a pipe that comes up here. Now we fill this thing with water, and so it's filled up all the way. They're all open to the atmosphere, and so they should be at the same fill level, which is about, about that much. Now, here's a question. Um, at which point, we can call that one, two, three, four, and five, is the pressure the greatest? And, pause the video, think about it. Maybe you'll think of an equation that will help you with this. And of course, the pressure at each of these points, one, two, three, four, and five, are all the same. And the reason for that is, um, let's get this. The reason for that is pressure is equal to atmospheric pressure plus rho gh. And they're all the same. H is the same for all of these, with H being this depth from the fill line to that point. So interesting thing to think about. Sometimes we think about, you can think about pressure at a depth as like the weight of the fluid above it. And so this one appears to have more weight above that point. This one appears to have, let's say, even more weight. This one appears to have less. So thinking about it that way can kind of confuse you here, but it's just based on depth. We can talk more about that, but I'm going to move on. The next thing is called Pascal's principle. And I'm going to start with the picture first. If you take a look at the picture, we have a tank filled with water. And over this water, we put a plate or something. If this is a round tank, we'll put a plate over it that completely contains or confines the fluid beneath. And this plate that we put over here has an area A. And what we're saying here is, what if we apply a force to that plate? We put some masses on top of it or something to push it down. Well, that's going to change the pressure in the fluid below it. Now, before, when we are looking at our previous example, our pressure here is rho gh, and yeah, if you wanted to add atmospheric pressure to it. But now when we add a force to this confined fluid, we're adding extra pressure. And so what happens here is that, mm, let's call this, oh, I don't know, let's call this pressure two, and this is pressure one. When we confine the fluid and we add force to it, we're going to increase the pressure of this point and this point. In fact, all points, we will increase the pressure of that fluid. So it says here, a pressure change applied to a confined fluid is transmitted undiminished to every point in the fluid and to the walls of the container. So that is Pascal's principle. And here's an example. Here's a practical example of how this is used. This is like a hydraulic system in a mechanic shop. And so let's say you want to lift a car. And one way you can do this is with a hydraulic jack. So you put like a kind of like a big piston here, which will hold the car up. The car has a mass of 900 kilograms, sitting on some fluid, typically oil, and it's got a line that goes over here to another little piston that we can push. And the area of the pipe here is 0.03 meters squared, and the area of the pipe over here is 0.0003 meters squared. Now, going back to the horizontal line concept, okay, let's say this thing is at rest and nothing is moving. Pressure at point one is equal to the pressure at point two. Okay. And what we could do is up here we have like another little piston we can push down on this fluid. And I guess the question we want to figure out is how much force do we need to apply to start to get this car to start moving up? Liquids are incompressible, and so when you push on this down here, this fluid here will rise and push the car up. So the pressure at point one, we're going to ignore this little amount of fluid here. As this is the piston is right here at P1, but we're going to ignore this. We're going to say that's a negligible amount of fluid in there. And so we'll say the force F1 applied over the area of A1, okay, it's the area of that pipe right there, will be equal to the force pushing up on the car, F2, over A2, the area of this pipe here. Now, we know all of these things except for F1. So, well, we're trying to find F1. Let me rearrange it first without, we'll say F2, and then A1, and then A2. We just multiply both sides by A1. So we'll say the force that we need to apply to raise up that car is F2. Now, what is the force on this piston here? Is mg of the car, so that's 900 times 10, that's 9,000 newtons. A1, the area is 0.0003 meters squared, and then area 2 is 0.03 meters squared. Cool. And of course, I don't have my calculator handy, but let's grab it over here. $9,000. Oops. Of course, and then I erased everything. Cool. And F1, the force that we need to apply is 90 newtons. So it appears like we have like a force multiplier. Setting up this system here, this hydraulic system is like a force multiplier. You push with 90 newtons, but yeah, you're pushing up a car at 9,000 newtons. And this is just an example. It seems like you're getting something for nothing, but in terms of energy, you're not. There's no friction here anywhere. You're getting an equal amount of energy. You're not getting anything for free. And so we say like the work, you can say the work that you do, your force times your distance. Let's do it this way. Little force times a big distance. Over here, the work done is virtually the same, but it's a big force over little distance. In other words, you're going to have to pump this over a much longer distance to get this to move just a little bit of distance. So we're not going to use that, but over here, this is typically what we will use for these types of problems. Okay, what's next? Yes, okay. So our next topic is buoyancy. So we'll come to Archimedes' principle here in just a minute. But buoyancy. Um, Buoyancy, of course, is when something floats. We say it's buoyant, okay? Even when something doesn't float and let's say you throw a cube and it starts sinking in the water, it still has a buoyant force on it, okay? So let's keep it simple. We just dropped this cube in the water. There, yeah, gravity is going to bring this down, mg, gravitational force, but there is a force pushing it back up. We call that the buoyant force. And so in this illustration, we're just trying to show what causes the buoyant force, and it has to do with pressure. So let's call this like H1. So there's a pressure here. We can call it P1 is atmospheric plus rho g H1. But, the pressure midway, let's say, call that H2. Pressure 2 is atmospheric plus rho g H2. Because the depth is greater, then there should be a greater force. So somewhere the point P2, up here the point or the pressure P1. And then of course down here is P3. We can keep going with this. It's atmospheric plus rho g H3. Of course, H3 is an even greater depth. My point here is that pressure increases with depth, but that relates to the force. Okay, so there is a greater amount of force down here at the bottom than pushing on the top. And that force kind of differential is what causes the buoyant force. There's much greater force pushing up on this thing than pushing down on it due to the water. And we call that that effect the buoyant force, pushing it up. So it might have been a long way of explaining something a little bit more simple. Okay, let's talk about Archimedes' principle. Archimedes is credited figuring this out. Buoyant force on an object is equal to the weight of the fluid displaced by the object. What we mean by that is here's a cube in the water. You can imagine that this cube is occupying this area 2 times 2 times 2, which is 8 meters cubed. And this cube is displacing, it's essentially pushed out a volume of water that's 8 meters cubed. If this cube was floating, which I might come back to, um, great, I'm trying to copy it. If this cube was floating, let's say about right here, then it's not displacing the full volume of the cube. It's displacing less volume of water there. Um, it's essentially displacing like this much fluid. But Archimedes said, if you weigh that fluid that it's displacing, in this case, the whole thing, or in this case, partial, you take the weight of that fluid, that is equal to the buoyant force pushing up on the cube. And so we write that like this. Buoyant force, FB, is equal to rho VG, sort of stated. It's equal to the weight of the fluid, mg, but mass is rho times v. So this is the density of the fluid. This is the volume of the displaced fluid, which is not always equal to the volume of the object, keeping in mind, and then times g. So let's do an example. And for this example, I'm just going to look at this cube that is submerged in the water. The buoyant force is equal to rho Vg. Now, in this case, the volume of the displaced fluid is equal to the volume of the cube. So we'll say density of water is 1,000. 2 times 2 times 2 is 8 meters cubed. And then G is 10. So this looks like 80,000 newtons is the buoyant force. And, I could have shown in here a step where I say 1,000 times 2 times 2 times 2, times 10. I could have shown that. Yeah, I'm going to go ahead and give an example. What if this thing is floating here and exactly half of it is balanced like this, so that half of it is under the water and half of it is above the water? And that didn't work out as planned. So you're just going to have to imagine it. Well, the buoyant force is different then. It's rho vg, 1,000. But the volume of the displaced fluid, and what I'm saying is it's 1 meter of height through the cube there, v2 times 2 times 1. times G. So this is 40,000 newtons. Hopefully you get my point. It depends on how much fluid is displaced. Okay, let's go to the last one. This is apparent weight. Sphere of radius 0.4 meters and mass 400 kilograms is submerged in water. What is the weight of the sphere? So this is nothing special. The weight is simply the gravitational force of the sphere. The mass is 400, G is 10, so it weighs 4,000 newtons. What is the buoyant force on the sphere? Whoops. So FB is rho VG. The whole thing is submerged, so it is the volume of the sphere. This is the displaced fluid, that's 1,000. Now, what is the formula for the volume of a sphere? This would be 4/3 pi um, r cubed, and then G is 10. So I should have just substituted the radius in there. So we'll do that here. So that's 1,000 4/3 pi. The radius of this thing, 0.4 cubed times 10. And we'll just calculate it. 1,000 times 4/3. 2681 newtons. Looks good to me. What is the apparent weight of the object in water? Okay, so the point of or what this means is this. The sphere is in the water, it's got a buoyant force on it. Um, this is what we mean by this. So if imagine you take an object and you place it in water and you're trying to lift it out of the water. When it's in the water, it's going to feel like you're lifting less weight. It's going to feel lighter. Okay, we call that apparent weight. So this is how it goes. This is seen this written different ways. F apparent is equal to mg minus b. Sometimes we resort to FA, F apparent, but let's keep it consistent. F apparent is equal to the weight, mg, that's 4,000. FB is 2681. So the apparent weight is 1319 newtons. It will appear to weigh that much. Another way of looking at this is like, let's say I had a spring scale and we had that mass. Oh, it's a sphere, right? Here it is. And over here we have some water. So when I weighed in air, when I'm just holding that spring scale in that sphere here, the spring scale should read 4,000 newtons. Now, but if I take that sphere and I now put it in water, the buoyant force is essentially taking off some of the weight of the mass, and so it's going to read less, and that's what it will read, 1319. It's the apparent weight in water. Anyway, and that is it. That's the second video on fluids. I think we covered everything. Yeah.